Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at Boolean algebra. So Boolean algebra differs from ordinary algebra. In ordinary algebra, we use numbers and we use the operations like addition, subtraction, multiplication, division. We use raising to a power, etc. But in Boolean algebra, we're operating on only two symbols. The only numbers we consider are 0 and 1. Now, 0 corresponds to false and 1 corresponds to true. Now, the operations we use are here. You've seen these logical symbols before. Negation, this one is conjunction or and, disjunction or, and this is exclusive or. So here, negation corresponds to complement, and corresponds to times, and or corresponds to plus. This one, exclusive or, corresponds to addition modulo 2. So let's look at calculations in Boolean algebra. So let's start with 1 plus 1. Now, obviously in normal algebra, that equals 2. But here, we don't actually have a symbol 2. We only have 0 and 1. So 1 plus 1 is going to be either equal to 0 or 1. Now, we can replace the plus here with the operator or. So this is like saying 1 or 1. So how do we determine what this is equal to? Well, let's look at this Venn diagram here. So I've put truth values for A and B. In this part of the Venn diagram, A is true, B is false. We're in A, but we're not in B. Of course, in the middle, we're in both A and B, so both A and B are true. In this part, A is false, B is true, and of course, outside the Venn diagram, both are false. So here we're looking for 1 or 1. Now, the operations here are commutative. That means the order doesn't matter. So I can let this refer to A and this refer to B. Wouldn't have mattered if I chose them the other way around. So here we're in A, we're in B. Is it true that we're in A or B? Well, that's obviously true. So 1 or 1, in other words, 1 plus 1 in Boolean algebra is 1. If A is true, B is true, A or B is definitely true. All right, let's look at this one here. So here we have not 1 and 0 XOR 1. Now, in order to calculate this correctly, we have to be clear as to the order of operation. So just like normal BidMaths, we do anything in the brackets first, and then we follow this order of precedence. So the first thing we're going to do is 0 XOR 1. So XOR means exclusive or. It means A or B, but not both. So this one's telling us we're not in A, we're in B. Is it true that we're in A or B but not both? Well, clearly that's true. We're in B but not A. So this becomes 1 because it's true. Now we do this operation, negation, before and. So the negation of 1 is just 0. If it's not true, then it's false. False has a value of 0. So this is 0 and 1. So now it's like we're saying A is false, B is true. Is A and B true? Well, it's clearly false because and requires both of them. We have B, but not A. So our final answer here is 0. So we can also evaluate expressions like this because true is just 1 and false is 0. So we could write this here as 1. Now, or is plus 1 plus 0 and the negation of 0. So let's go and perform those operations. We'll perform the brackets first. So 1 plus 0 is just 1. And now we do the negation next. The negation of 0 is 1. So the negation of false is true. So we get 1 and 1, and that is, of course, 1. All right, let's now look at a question involving a proof. So we want to prove that the complement or negation of xy is equal to the complement of x plus the complement of y. So we're in Boolean algebra, so x and y can each take a value that's either 0 or 1. So just like in ordinary algebra, xy means x times y, or x and y. We can write this first statement as the negation of x and y. And we know from De Morgan's laws that this is equal to not x, negation of x, or not y. Now, De Morgan's laws can easily be proved in logic. We've just applied them here. You can also prove it by drawing and shading a Venn diagram. Now, of course, not x, we can just write as this. And remember that or corresponds to plus. So here we have proved what we set out to. All right, let's now take a look at logic gates. So computers are made up of billions and billions of transistors. These are tiny switches that are either on, corresponding to 1, or off, corresponding to 0. If they're on, they send electrical signals, and that's how your computer performs tasks. So, logic gates are an important interface for this. See, logic gates are patterns of transistors that are wired together. And these form the building blocks of digital circuits like CPUs. So important that we can understand them. Now, in logic gates, we use these symbols here. Now, we can determine the output of a logical gate using a truth table. So let's look at this logical gate here. So here, A, B, and C are inputs into the circuit. D and E are outputs that form the inputs of the last gate, and our final input is F. So firstly, when presented with a logical gate, we need to understand all the gates. So this one here you can see is the gate for AND. So the one down the bottom is the gate for NOT. And this one here is the gate for XOR, exclusive OR. So let's go ahead and determine what the possible outputs of F are. So the inputs A, B, and C can either be 0 or 1. So the total number of possible inputs into the circuit is 2 times 2 times 2, which is 8, and I've listed them down here. So let's figure out what D and E would be first. Well, D is just A and B. So that means A has to be 1 and B has to be 1. 1 and 1 is 1. 1 and 0, or 0 and 0, is 0. So D will be 1 here because A and B are 1. It will be 1 here because A and B are 1. And it will be 0 elsewhere. All right, what about the output that is E? Well, it's just not C. It just has the opposite pattern here. So here C is true, so that means that E will be false, and so on. So now we can determine the output F. So F is exclusive OR. Again, it's going to be D or E, but not both. So this first one is D or E, but not both. So F will be true. Here we have both D and E. XOR excludes. That's what the X means. It excludes the case where both are true. So this will be false. So here we have D and E, neither are true, so F is false. F is true when one and only one of D and E are true. So F is going to be true here, false here, true, false, true. This gives us the possible outputs of F for all possible combinations of inputs A, B, and C. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.